Okay, welcome to the video of Laplace Transforms. There's quite a bit of information that's going to be presented here, so I'm going to have to split this up into two different videos. One's going to be just your general definitions and how you use Laplace Transforms, and the other is going to be based on taking the Laplace transform of a derivative function. Ordinary derivatives and the partial derivatives is kind of what we're shooting for. So let me first start by saying you've seen this is the standard wave equation that we've seen in the past. Using separation of variables, we've been able to do this. This lent itself to being solved by separation of variables because, in particular, because of the boundary conditions being held at zero. But we will see in the near future that these boundary conditions don't always have to be zero. As a matter of fact, they can be anything. And ultimately, the point of the Laplace transform is to develop techniques for solving another way of solving differential equations, whether it be partial differential equations or ordinary. And the idea here is that with Laplace transforms, it makes it a lot easier to come up with solutions for these equations instead of separation of variables. So what we've seen in the past is this wave equation that we have here. We can apply a Laplace transform on this. However, if you notice, we're looking for solutions of u, x, and t here. You notice that these solutions have two input variables, x and t, which is why we were able to use the method of separation of variables in the past. But applying a Laplace transform on this wouldn't make any sense if you don't, or if you can't remember how to do Laplace transforms on one input variables, which is why I have this other differential equation here. So this is a partial because I have two input variables. This is a ordinary because I have just one input variable, meaning I'm looking for a function of y of t. I've just given you two different types of differential equations here so that you see the difference between the two. This video will actually cover specifically how to do Laplace transforms on functions with one input variable at a time. So I should probably establish a couple things. First is that in order to do a Laplace transform, first of all, Laplace transforms can only be used on functions. They take a function and they transform it. If you look in the textbook, I believe it's in chapter 4, which is kind of what I'm reviewing here. A Laplace transform will take a general function, in this case y of t, but it could be any function, t of t, not a t of t, y of t, f of t, x of t, any function like that, and it applies, here's the notation, it applies on a function y of t, in this case, and it actually transforms it, meaning it does some kind of mathematical computation on it. And the computation is specified by taking the integral from 0 to infinity e to the minus st times y of t dt. So there are a couple ways to actually look at this, and the easiest way is, what does a Laplace transform do? Well, it takes a function y of t and it multiplies it by e to the minus st, and then you take the integral of that product from 0 to infinity of dt, and what you wind up getting is some capital Y function as a function of s. And you might be thinking, well, what happens to the t's? The t's go away because they get evaluated. This integral is with respect to t, and it gets evaluated from 0 to infinity. So there are a couple of restrictions here. The t variable must be greater than or equal to 0, and that's the only time you can use Laplace transforms. If this condition is not met, then you can't use Laplace transforms to transform this function into some other y function of s. And you'll notice as we go down the road that this u of xt, the heat equation and the wave equation, are both equations or both types of partial differential equations that you can use Laplace transforms, because the fact that t is a variable that starts off at 0 and goes to infinity. So this is the basic definition of Laplace transform. It takes a function y of t, and this is the notation, by the way. It multiplies that function e to the minus st and then integrates from 0 to infinity, and you get some other function y of s. So I'm going to do a couple of examples here. And let me just give you an example of, instead of y of t, let's just use a function f of t, and let's suppose that that's equal to 1. So if that's going to be equal to 1, then the Laplace transform of the f of t is the same thing as the Laplace transform, or just substitute your f of t, so you get 1, which is a constant, but it's okay. And all that does is takes the integral from 0 to infinity, e to the minus st times 1 dt. And as you've seen this before, and perhaps calculus 2, where you're taking the integral of e to the minus st, you would integrate this as you would any other integral with respect to t. So this winds up being minus 1 over s e to the minus st evaluated from 0 to infinity. And what that winds up being evaluated as, if I can simplify this to minus 1 over s e to the st, all I've done is I've taken this exponent and rewritten this e to the minus st in the denominator because I can. And that's going to be minus a minus 1 over s e to the st. And this whole thing's going to be evaluated from 0 to infinity. And the way you do that, maybe I shouldn't do that, hang on. Let me rewrite this as the individual function. So this is going to be actually evaluated as the limit as t goes to infinity. Now I can go ahead and do what I did earlier. Minus 1 over s e to the st. And I'm going to put minus a minus, which is going to be a plus, 1 over s e to the s times 0. And that is going to be equal to, well, if you go back and look at this first term, as t goes to infinity, this exponent here is going to explode, and this exponential will explode as well, which means that the denominator will explode, and this whole term will wind up going to 0. And what we wind up having left is just the 1 over s. And this is, so that means that this winds up being the Laplace transform for the function 1, I should say when f of t is equal to 1, is just equal to 1 over s. And if you'll notice, this right here is a function of s. So since we started with a little f of t, the notation, the standard notation is to say capital F as a function of s. Notice there are no more t's here because they've been evaluated out. Similarly, we can say that if I do another example, let me change this to another example, say f of t, let's suppose f of t was equal to t, and I wanted to do a Laplace transform on this. What I could do here is say, same thing as before, Laplace transform of f of t. What is that going to be equal to? By the way, these are braces. Let me see if I can put this a little bit better here. These are braces, and that's the standard notation for a transform of Laplace. Let me rewrite this as substitute the f of t with a t, because that's what f of t is equal to, and that's going to be equal to integral 0 to infinity e to the minus st. I think hopefully you're seeing the pattern here, times t. This is your f of t function, dt. At this point, if I wanted to actually calculate the integral, and I'm going to go ahead and do that just to show you where they're getting these Laplace transforms, from, I can say that's going to be equal to this right here. You would solve this by integration by parts, where I would set u equal to t and my v prime equal to the e minus t, in which case v would be minus 1 over s e to the minus st, and u prime would be just equal to 1. So then this integral up here winds up being equal to u times v, which is minus, let's call this, the product of u and v would be minus t over s e to the st. I've done some simplification here. And that's going to be evaluated. Note that I'm doing the evaluation up front here. Evaluated from 0 to infinity, and that's minus the integral from 0 to infinity of u prime times v, which winds up being 1 times negative 1 over s e to the minus st dt. And if I carry out this evaluation, focus on this first term first. That's going to wind up being equal to the limit of t going to infinity minus t over s e to the st. That's the first part. Minus a minus, which is going to be plus t over, maybe I shouldn't put t, actually I should evaluate that as 0. 0 s e to the s times 0. And this right here is just this first term up here. So minus, and actually I can pull this negative out to make this a plus, and pull the 1 over s out because that's a constant with respect to t anyway. Integral 0 to infinity of e to the minus st dt. Notice here, keep evaluating, you wind up getting the limit as t goes to infinity. Now you might look at this and think, well, both of these are going to go to infinity, but this exponential will explode at a much higher rate than this t will. So in the end, this denominator will wind up being much larger than this t will, so this whole thing will go to 0. And of course 0 over, well, this winds up being 1 over s times 1 is going to be 0, so that goes away. And what we wind up having left is 1 over s from 0 to infinity of e to the minus st, and I'm going to actually throw in, there's a 1 function in here, dt, because I can go ahead and do that. Recognizing that in the previous slide, this right here wound up being equal to 1 over s. This is the transform for the 1 function, which is 1 over s. So we wind up getting is 1 over s, which is this one right here. And this transform integral here winds up giving us 1 over s. So what we wind up having is 1 over s squared. I've just given you a couple of examples of how to do transforms, what I would call the long way, by actually muscling your way through the calculation of this integral of 0 to infinity e to the minus st times that function that you're trying to transform, dt. To make the long story short here, we're actually going to give you 7 standard functions or common functions that we often see in doing transforms. If you notice, we did this one, the Laplace transform of 1 is 1 over s, and we also did, which one was it? This one here, where the Laplace transform of the t function, where n was to the first power.